Hello. So I wasn't able to attend the meeting in the morning because I had some issues going on. But this Lab 7, is actually pretty easy. It's something you can do in 5 minutes and then make your lab report, which doesn't need to be in too much detail because, as as I said, it's a pretty easy one. So I'll just go over what you have to do. If you have any questions, you can email me. Um, uh, and if you have questions about the other labs as well, you can you can email me. So I will quickly go over what you have to do. The document, by the time you watch this on YouTube, should be on Blackboard. So, and you will have 1 full week to complete this. By the way, it's something you can complete within 1 hour with the lab report. All right, so this is the document. Lab 7 is electrical equivalent of heat. This was something we were supposed to do last week, but because of the fall break, we're 1 week late. Okay, so what you have to do here is, all right, so if you were in person, what you would have done is you would have taken a beaker of water, we would have heated a resistor, and we would have seen, how how much heat is dissipated by the resistor. Now, most of you have had mechanics before, and you know this relationship that energy is power times, the elapsed time. T here is elapsed time, P is the power, and E is the energy. So that is the energy that will be dissipated by the resistor. And electrical power is voltage into current. So that is what we call electrical power, voltage multiplied by current. Now, the energy gained by the water that is being dissipated from the resistor is given by this relationship. Again, this is a pretty, one of the most basic relationships we have in thermal physics, that the energy is equal to mc delta T, where m is the mass of the water, C is the specific heat of the water, delta T is the change in temperature. And C here, specific heat, that's like, I think definition would be something like the amount of energy that you require to raise the temperature by 1 degree Celsius of a unit mass of some material. So that is specific heat. And it obviously for a material, it will be a constant because it's per unit mass and you're raising by that constant amount, which is 1 degree Celsius. All right, so these three equations, that's all you need for this lab. And if you'll click on this link, follow these instructions, and you have this table, you'll get everything from the simulation, and you have to compare your final answer to this value that you have here. Show all calculations and answer the three questions that you have at the end, which are pretty simple. And this is it for the lab. Now, I will now move on to the actual simulation that we have. When you click on that link, you will see this. And so you click begin and you will see this. So this is our simulation. This is the virtual power supply. And you click power on, it shows some voltage in volts. Now you can change the voltage. As you can see, click power off. You can turn the dial and it's now decreased to 44. And again, you click this side, it's going to increase. Click power on again, it's back to 83. You can, now it's 101. So you can change the voltage, and our virtual ammeter gives us the current in amperes. So right now you can see it's around 7 amperes. So 101 volts and 7 amperes, which means you have the current, you have the voltage, so you know the electrical power. So, okay, you have this. You can change the volume here of water by clicking on this beaker. So as you can see, you click, it increases, then it goes back down to 200. So you can change the volume of the water, and you have the temperature. So look, you click on, right now it's around 6. It's increasing, as you can see, pretty quickly here because we have a high voltage and high current, and the time elapsed is given here. Time 16, 17 seconds elapsed, and then you turn off at some point. And you will have some final temperature. So if you go back to the document, you will see it says press begin, and it says volume should be around 200. So do that. Set voltage is 6 volts or at least 22. So 6 or 22. I think that those are the options. Push the on button on the power supply. Yeah. Okay, so you have to wait until it rises 5 degrees Celsius. So you have to wait. So delta T is already given to you. That is 5 degrees Celsius. And you can start from 16 to 21 or 21 to 26, but it should be 5 degrees Celsius. And once you have that, you will have some volume of water, which is given in the simulation. Density of water, we all know, is this. So you can find the mass from the volume and density. Power supply is voltage into current, as we discussed. Temperature maximum and minimum. Change in temperature will be 5 degrees Celsius. And electrical energy is power into time. Now, power is just voltage into current, which you already have. Multiply that with the time elapsed, you get electrical energy. Thermal energy is given by M, which is the mass of the water. C, specific heat of water, which I think was given right here. So you have this. And you have delta T, which is again the change in temperature, which we also have. Now, something you could do here is keep everything in grams. We usually don't do this in physics. We want to change everything into SI units, but in this case, because the specific heat is in these units here, grams, and density here is in grams per milliliter. So maybe you want to keep it in grams, or maybe you want to convert everything into SI units first. So that's your choice, whatever is easier for you. But if you keep everything in grams, then you don't have to change the density into kilograms, into kilograms per meter cube or something, and then you don't have to change this into some form of SI units. So once you have that, as you can see, electrical equivalent of heat is electrical energy over the calories, which means you have this over this. So your electrical energy over thermal energy, that should be equal to this value. This is the theoretical value, and you will write your percentage difference here. And then you show your calculations. There will be not many calculations, like 2 or 3 lines. And after that, you have these 3 pretty simple questions. That they're asking about the simulation. So yeah, in the end, it's a pretty simple one. We probably didn't even need to meet for this, but yeah, I got stuck up with something else. So sorry about that. But if you have any questions about this lab, you can email me. But again, this is a pretty easy one, probably the easiest lab you will have this semester. So okay, this will be it for lab 7. Again, just email me if you have any questions. I'll see you next week.